Hi, Isaac here. Have you ever wondered what it takes to fly a satellite? Well, in this video, we're going to be talking about what a spacecraft link is and why it's so important to all satellite missions. But before we get started, be sure to hit that subscribe button and notification bell too, so YouTube tells you when our videos come out. Also, hit that little thumbs up button to help spread the word. And as always, if you have any questions about the video or any of its content, leave a comment below and I'll be sure to get to it as quickly as I can. For this video, let's take a very high-level look at what a satellite data link is and the major system components needed. The objective for any mission is to send data to and from the satellite. For that, you need something called a data link. This can also be referred to as just a link. At its most fundamental level, you have 5 layers that make up a link: the satellite layer, the antenna layer, the SGC layer, the server layer, and the workstation layer. At the satellite layer, we can have one or more satellites. When you have more than one satellite, they can collectively be referred to as a constellation of satellites. The satellites are the entire reason to have a mission in the first place. For example, the GOESR mission is to provide science data to assist in weather monitoring and prediction for the United States. In order to receive or transmit signals to space, an antenna is needed. Depending on the size of the mission, some smaller missions may not have dedicated antennas. So instead, they have to rent time on existing antenna systems. GOESR has 6 dedicated antennas capable of transmitting and receiving signals. At the time of this recording, GOESR also has 4 additional antennas. These antennas are for receive only. As we discuss SatOps more and more, you'll start to see some common themes pop up. The first of which is redundancy. It costs a lot of money to put a satellite into orbit. So it's critical to have enough redundancy to ensure that we can capture all of the data in the event that there is an antenna failure. Next is the SGC layer. SGC stands for Space Ground Communication Equipment. This layer is responsible for many things related to processing the signal. It converts the data from an analog signal to a digital signal and vice versa. It's also responsible for packetizing the data before it's sent to the satellite. The SGC also does things such as routing, encrypting, setting the data rate, and properly modulating the signal. Depending on the mission, the SGC may be put in the antenna layer or even the server layer. But because they are responsible for so many critical functions within the data path, I like to pull them out and put them in their own layer. Once the data has been converted from an analog to a digital signal, the standard IT infrastructure and techniques can be applied. Satellites generate a lot of data, so it's not uncommon for missions to use server farms in order to handle and process all of that data. The first thing that needs to happen when data enters the server layer is that it needs to be archived. Data archival for satellites is really important since you can't regenerate any of that data. The first rule of SatOps is don't drop the data before archiving it. Beyond archival though, many other mission applications and processes that are necessary for mission functions are located at the server layer. And the final layer is the workstation layer. This is the layer where humans interface with the system. It's where the satellite operators will send commands and monitor the constellation. This is also where the engineers will perform their daily work, such as data analytics of their particular subsystems, writing scripts to improve performance, and testing new products before they put them into the production line. Let's say we want to send a command to the satellite. This command typically originates from an operator entering the command into a workstation. The workstation then forwards the command onto a server. The server then sends the command over to the appropriate SGC hardware. The SGC converts the digital signal into an analog signal and then sends it to the correct antenna. And finally, the antenna transmits that signal into space to be received by the satellite. This entire process that the command data goes through is called the uplink path. When a satellite sends back data to the ground, it goes through the exact same process, but in reverse order. That's called the downlink path. And for more complicated satellite constellations, the satellites can send data between one another. This data transfer between satellites is called a crosslink path. GOESR uses a crosslink to receive data from the GPS constellation. Typically, there's only one antenna transmitting to a satellite at a time. This means that there should only ever be one uplink path. However, this is not typically the case for the downlink. On the downlink, we want as much redundancy as possible in order to avoid dropping any data. So to make this happen, there are typically primary and secondary data paths that can receive the data. Each path uses a different set of equipment. This full data path is referred to as a link. And depending on the mission, there are usually multiple links per satellite. As an example, let's look at the GOESR series satellite. There are several uplinks, downlinks, and crosslinks. For this mission, the links are based on the type of data being transmitted. From the satellite operations perspective, there are 4 main uplinks, 7 downlinks, and several crosslinks. For uplink, there are 2 command links. These links are always online and broadcasting a signal to the spacecraft. However, data is only transmitted as needed, so basically whenever we need to send a command to the satellite. The other 2 uplinks are for the GRB, which stands for Goes Rebroadcast. This uplink is continuously sending processed weather data from the ground system to the satellite. The satellite then bounces the signal back down to Earth. This method of receiving a signal and retransmitting it back without altering the data in any way is called a bent pipe. By rebroadcasting this weather data out to the entire Western Hemisphere, anyone can now receive weather data, even including ships that are out to sea and don't have easy access to the internet. It's really cool when you think about it. For the downlink, there are 2 spacecraft engineering telemetry links. These links are the primary source of engineering data for all the satellite engineers that manage the health and safety of the vehicle. As for the science, all of the raw science data gets downlinked over a single link. There is a lot of data on this link, so it requires a pretty big pipe compared to the rest of the spacecraft. The pipe is big enough that even some higher rate engineering data is put on it. Next, there are 2 dedicated downlinks to receive the GRB that was originally uplinked. This allows the engineers to see what the customers should be seeing when they use their own antenna equipment to downlink that GRB data. And lastly, there are 2 auxiliary communication downlinks. GOESR has a secondary mission objective where it acts as a relay satellite for things like search and rescue. Finally, there's the crosslink. As was previously mentioned, there exists a crosslink between GOESR and the GPS constellation. GOESR is constantly listening for any signals it can see from the GPS constellation. Just like your phone, GOESR uses the GPS satellites in order to determine its own time and position in space. In order to do this, though, it has to be able to see a minimum of 4 GPS satellites. Realistically, GOESR can see something like upwards of 7 GPS satellites at any one time. Each one of these uplink and downlink paths needs to pass through all 5 layers of the link in order to transport the data successfully. As systems grow in scale and complexity, managing these links can be a real challenge. There are a lot of moving parts and many interfaces, all of which must be configured correctly in order to properly transport the data. Part of my job as a mission management engineer is to help manage these interfaces. Each layer has an entire team dedicated to operating them, so ensuring communication between each team is critical. If any one part of the layer is misconfigured, there will be a data outage. And depending on which layer is misconfigured will greatly affect how impactful the outage is. Let's say, for example, that a component critical to receiving the satellite transmission signal within the antenna fails. Well, if that antenna fails, any SGC that happened to be listening to it at the time of the now failed antenna will no longer be able to receive any of the data. This will have a cascading effect downstream and potentially cause major data outages. This is why having a secondary backup link is so important. The bigger and more complex the system is, the higher the chance some random component in the data path will fail. Fortunately, hardware failures are rare, but they do happen from time to time. and they usually happen at the worst possible times, say 3 in the morning or on a holiday. Those phone calls are never fun to pick up, but SatOps is a 24/7 job, and for GOESR, people's lives are on the line because weather can be deadly. So you pick up the phone and you roll with the punches. In future videos, we'll discuss how you can make a link configuration more robust in order to minimize those outage times. We'll also be diving deeper into what exactly makes up each layer of a link. There's a lot to keep straight. Links can be tricky to wrap your head around, but at their highest level, they're just a data connection between the user and the satellite. Thanks for watching. If you liked this video, hit that thumbs up button. Make sure to subscribe and hit the notification bell so YouTube tells you when we post a new video. If you have any questions, please leave them in the comments below, and I'll see you soon in the next video.